We're back with another video. Today we want to talk about materials, a little bit about material science and why we choose what materials we do for what components.
Yep.
And dive in specifically about, we'll touch on plate, castings, forgings, and mechanical properties of the materials that we use, and as well as what we anticipate going to in the future, and talk about some future plans on stuff. So Eric, you want to lead us off? You put together this outline for the most part.
Yeah, so I guess one place to start is just to kind of define some mechanical properties so that as we talk about them, you'll know what we're talking about. So a lot of this, when we're looking at a material, a good visual representation of a material's strength is going to be its stress-strain curve. So starting with stress, what is that? That's force over area. So same as pressure, that's going to be measured in pounds over square inch. So if you have uniform force, the smaller area you have that force over, the higher the stress. Strain is going to be elongation of a material, deformation. We're going to measure that in percent elongation. And then two common strength markers that you're going to see are yield strength and ultimate strength. Yep. So when you look at a material under stress or a material under strain, you can kind of look at it both ways. There's going to be an elastic and a plastic region. So the first thing that's going to happen is there's going to be a linear relation. We're talking about metals right now. A linear relation between stress and strain. And we'll put a graphic up, so because this seems ridiculous just talking about it without a visual right now, but it'll make more sense with that. Yeah, you'll have stress on your y-axis, strain on your x-axis, and you're going to have a linear relation between the two up until what you call the yield point. So if you keep it under this yield point, you load a material up, it'll elongate, stress will go up, and then once you relieve that stress off of the material, it'll come back down in a linear fashion. So that's why it's called elastic. The material goes back to where it came from. The yield point is defined as 0.2% strain, at least in the US. And what that means is you've started to go to a plastic deformation of the material. And so once you get past this yield point, you're permanently deforming the material. And so now you're no longer in a linear relation, it's going to start to arc over. And so you load this material, you get into your plastic region. Once you unload it, now you're going to have a linear relation, or a line that's parallel to your original line going back, down to zero. So basically whatever the difference between those lines is, that's how far you've permanently deformed this material. So when you're in your elastic region, you can use your modulus of elasticity or Young's modulus to see how much will this material move under a load. And then when you're in your plastic region, you're looking at ductility versus being brittle. So percent elongation at break is typically the measure that we're going to look at. Density is another one. So that's just a fancy way to say weight of the material per unit of volume. And then thermal conductivity is the other one that we're looking at. That's rate of heat transfer through the material over time. So,
and those all come into play for a varying number of reasons. So where do we want to start as far as material goes? I think it's worth noting right off the bat that we use two different alloys for all of our production stuff in both our race application as well as our bolt-on applications. So every box that we make, whether it be for our 2-gear crawler or our race stuff that goes on trophy truck or Ultra 4, or our bolt-on Jeep, Bronco, Tacoma applications, the box is always 60-61. And we've found through, both engineering analysis as well as over a decade of practical application and doing it it worked, did it break? I mean, there's multiple ways to test this, but I'm a big proponent of do the engineering first and then actually test it in real life. We don't see failures on a 6061 box. And 6061 has the ability to handle heat much better than 7075. It never turned out to be an issue on this stuff. We just don't have heat problems. But I guess where I'm going with this is what really matters is selecting the right material for the right application. And while 7075, to make a blanket statement like 7075 is better than 6061 because it has a higher tensile and yield strength, is kind of missing the point and oversimplifying something. And this lesson was really ingrained in my head years ago. So if you want the best axle shafts possible, you make them out of 300M, and then there's a whole tempering process to heat treat and then temper it back down. And 300M is known as kind of the industry standard for axle shafts in high torque applications. You can heat treat it to a higher Rockwell hardness. It has better toughness. It has better tensile and yield than the lower grades of 4340. But if you want to make, say you want a wheel stud, well, 300M is the best material out there. It's the toughest, hardest, strongest material. That's a true statement for a certain application, which would, in this case, be an axle shaft. But there's always going to be more to the story. So 300M does have a tendency, because 300M is a modified version of 4340, you'll have a tendency of that material to work harden. So if you cut threads in a 300M wheel stud and you run that impact over that lug over and over again, you'll end up work hardening the material, and you'll hit what essentially what you'll do is you'll re-harden that material up to, let's say it can go up to 60 Rockwell, but at 60 Rockwell it's extremely brittle. So you'll be running and you think you've got these great wheel studs, and all of a sudden your wheel studs start snapping off and your tires go flying. Well, that's because the material inherently has a property that allows it to work harden. It's part of the alloy. So saying that 300M is the best material is like saying everything's a hammer. You can't, if you take that kind of approach, you're missing the nuances, you're ignoring certain properties that may or may not have a huge impact in the ultimate product. And what would you run for a wheel stud? Well, I would argue 4140 is a good choice because it does not work harden and it's still a strong material. So I'll circle back to 7075 versus 6061. They each have their place, and you have to know how to select which material for which application based on what are the forces and what are you trying to do with it. So it comes down to having a game plan ahead of time. So every upright that we make, whether that's for a race car or for a bolt-on product, is currently starts just like this. So this is Kaiser Select material. Kaiser Select is, well, Kaiser's a aluminum manufacturer. Kaiser Select is kind of their premium. It's a very expensive and very high quality grade of 7075 alloy. And we exclusively buy Kaiser Select because we want the best product that we can get for the specific application. And so everything starts out currently as a giant block of aluminum, and we kind of joke around. The parts in there, you just have to remove the extra material to get to it. So I think we kind of touched, is it worth talking about why we, Or do you want to add some clarity on why we choose 70-75?
I mean, it's application based if you're looking at it from a strength perspective. So,
Okay, so
yeah.
we'll probably have had this graphic up already, but it's worth comparing 60-61 and 70-75.
Yeah.
Tensile and yield.
Yeah, so yield strength on 6061 is going to be about 40 KSI. That means 1,000 of pounds per square inch. So 1 KSI is 1,000 PSI. So again, 6061 you're at about 40. 70-75 you're at about 73.
Yep.
Ultimate strength you're looking at 45 for 6061, 83 for 70-75. So it's significantly stronger on both regards. If you look at a box over here, so your main forces that you're going to see on this box are going to be from your bearings as a result of your gears turning, and then the wheel hub, and then your mating surface right here. So everything is really, it's compact. You're doing, what you would call a bearing stress on a material. So like when you load up this bearing, you're just compressing the material, the bearing's pushing into the bore and compressing the material. Whereas when we're looking at something with 70-75, an upright or a knuckle, you have other members on it like steering arms. In the case of an upright, it's actually part of your suspension. It's suspending the vehicle. So now you're adding leverage to things, and the forces you're going to see on the material are much higher. You're asking it to do a lot more.
Yeah.
So that's a big reason.
One thing that's worth noting is elongation properties.
Yeah.
70-75 is not an extremely elastic material. It has an elongation of up to 11%, whereas, so it can bend 11% before it ultimately will take a different form.
Yeah.
60-61,
before it breaks,
60-61 is an 18%.
Yeah.
So, and that really comes from some of the mechanical properties of the alloy itself. It's got a high zinc content.
Yeah, and it's one thing to note, since we are in kind of a nuanced area, is that saying these material properties, it's like if you go on MatWeb, that's kind of a dictionary of material properties, and you look up, say, 4130 chromoly, you're going to get like 12 different options. And a reason for that is the material property. You can have the same chemical composition, and you're going to have different material properties depending on how it's been worked, how it's been heat treated. Talk about work hardening. So that's it. When we're talking about going from the elastic to the plastic region, then coming back over, like we were discussing before, now you've effectively raised your yield strength by there. So work hardening, again, more nuance, isn't always a bad thing. When you roll out material from a mill, you're strengthening it, you're strain hardening it, and that could be a desirable thing.
Well, and also I guess I should clarify, because I'm staring at that block of aluminum, and it says Kaiser Select 7075-T651.
Yeah.
We will not dive into tempers of alloys today, but that T651 refers to the heat treatment that this is that is done post rolling at a mill. So a T651 is an aging process where essentially what they'll do, they'll take it up to a certain temperature, they'll hold it at that temperature for a set period of time, they'll slowly bring that temperature down, and then all of the 7 series alloys are aged, where, I might be wrong on this, hopefully somebody corrects me in the comments, they're going to hold this material at like 120 degrees for 48 hours to age it back to a T7651. That's a whole nother conversation for another day that honestly I will probably never dive into.
Yeah.
Because what we do in these kind of scenarios is I will talk with somebody who's an expert in material science who works for Kaiser, because there's several different types of tempers that you can get this material in. The most common is T7651. So that's what we're buying because it's readily available. 7075, you can buy it in a T7351. There's a few others, but you can actually temper it to different spots on that as well.
Yeah.
But the tempering really does matter. And I guess can kind of segment into other materials and where we're hoping to head with this product. Because let me be super clear on this. Part of the reason that our stuff costs 20 grand is we're starting with a massive block of material and having to chip away with a hammer and chisel to get the part out of it. There is a much better process. There's two different processes that from a manufacturing standpoint are much more efficient. And those two processes are casting and forging. And it's essentially the opposite process, where in both casting and forging, you start with a negative, a die of the part, and you pour the substrate that you want to forge or cast into a mold, and out pops a almost complete part.
Yeah. And
so let's talk about castings. I guess, where do you want to start? You want to start with castings?
Yeah, and I guess, so casting, one big difference between them, casting is going to be molten metal, forging, it's still going to be solid and you're forming it into a shape is kind of the big difference between the two.
You can also do a molten and then forged, but so the easiest way to think of this is for casting, you're pouring a liquid in and it solidifies and now you have your part, okay? For forging, sometimes you're going to take a solid block and you basically are mashing the thing into the shape you want. Now you can also hot forge where you're essentially pouring, or you have a heated block of aluminum or whatever material you want to forge.
Yeah, it's super hot and you're squishing it all together.
Squish it together.
Yeah.
I think it's pretty cool videos to watch on YouTube. Yeah. There's lots of really cool forging stuff.
They're crazy.
And the big thing about forging is it's the key component there is it's done under pressure. Yeah. And we're talking about a shit ton of pressure. Okay, so
definitely. So
castings.
So as far as castings go, for our purposes, we'd be looking at sand castings.
Yep.
That's very common automotive process, where typically your tool is going to be what's called a match plate, where you're going to have the positive of, like, say you have this gear, very simplistic idea of it. Draw a line down the middle. Say that's a board. Half of the positive will be on one side of the board, half of the positive will be on the other side of the board. And then you smash this match plate into sand to create a cavity. And then you do that on two boxes, you put them together. Now you have a cavity that matches the positive. You pour metal in, it cools, and now you have your part. It's relatively cheap. I mean, one of the big things, when we're talking about forgings, your tool is actually physically doing the work on the material under these massive loads. For castings, you're pressing sand. I mean, it's still going to be abrasive, so you're still going to get tool wear. It'll be a different kind of tool wear. But one of the, like, when would you want to use a casting?
Well, there's lots of applications that castings make perfect sense.
Yeah.
And we're not going to sit here and say that castings don't make sense on a portal. We'll get to that point in a minute, but you look at every axle housing that's not stamped steel with a third member dropout, that's in every truck, off-road vehicle, etc. It's a cast center section.
Yeah.
They're strong.
Yeah, they are strong. And part of the reason why you want to use casting for a center section are all of the oil flow cavities inside of it. So one thing you can do with casting is create what's called a core. So say you want a hollow center inside of a part, you can have this cavity in the sand and you can put a core in the middle of it, so now the material will flow all around it.
And you can't do that with a forging because you can't press. If you put something in the middle as a cavity, and you pressed around it,
Yeah.
it would be stuck there.
Yeah, when you'd have to get it inside the material to begin with too to create that
Yeah.
hole. So that's one very cool thing that you can do with casting. Typically, when we're looking at automotive, we're looking at ductile iron. So this is going to be, or nodular iron. It's going to be different from a cast iron in that it's much more ductile. So
Yeah.
instead of like I don't know, throw some numbers out that probably don't exist, 4% elongation at break, you might get like 12, something like that.
What do we have, so cast ductile iron properties real quick. Yield
Yeah.
strength, 45 KSI. Ultimate strength, 65 KSI.
Yeah.
Modulus of elasticity, you've got 24,000.
Yeah.
Elongation at break, 12%.
Yeah. And one of the cool things about ductile iron is a lot of times they'll be called, like that's called ductile iron 65, 45, 12. So it's literally just tensile, yield, elongation at break. So the name has the properties in it.
That's
which
nice.
Is fun.
A little cheat sheet built in.
Yeah, exactly. So, but there are downsides to ductile iron and sand casting.
Yeah, well, so from a I guess the biggest downside to ductile iron that I see for our application is weight. It's significantly heavier than aluminum.
Yes.
And we'll talk about why weight is a major concern for us. The other thing that I think most people don't realize, but we do from a manufacturing standpoint, ductile iron sucks. And I'll clarify that. So ductile iron, because it's sand cast, you'll get sand embedded in the material. So you can't cut it with carbide. You have to use high-speed steel. And it's very abrasive. So while it cuts really good and it's strong, it's kind of hell on machines. And so you'll get this ductile iron powder that goes through your machines and essentially will take a really nice high quality machine and turn it into a clapped out pile of shit.
Yeah.
Over the course of several years. And you know, there's two different ways to look at this. Is it's just a piece of equipment, but if you want to keep your equipment nice, and you guys do care about nice quality equipment, because if you have a machine that is clapped out and there's been so much ductile iron go through the ways that now the ways are loosened up, and now you have a machine that doesn't really want to hold tight tolerance, that the implication of that is parts that are not really made to spec. That's on the manufacturing side, and
Yeah.
let's be honest, if you're outsourcing all that stuff, that's somebody else's problem, but somebody else's problem will always come back to be your problem, because at the end of the day, it's our product.
Yeah.
We have to own it.
Definitely. And then even just looking at, say we have this 6061 box right here. Say we want to make that out of ductile iron, like on top of the manufacturing side of it. Like let's say we just changed material on this. Well, your strength is going to go up by 5 KSI from 40 to 45 yield. And to be clear, we use yield for the most part because you're not plastically or permanently deforming the material. So you're shooting to be under that.
Yep.
So you gain, what, like 12% strength or something like that. But your density is going to go up by like 2.4 times. So the strength to weight doesn't really balance out there. There's not much you can do about adding that additional weight to the part.
And thermal conditions.
Yeah, that's another one. So if we're looking at rate of thermal conductivity through the material, 6061, 1160. I'm not even going to pretend to understand what the units mean. I just use it as a number.
Well, but it's worth noting because you're 4 times.
Yeah, it's 4 times. 4 times. So that's, and if we're going absolute, it's BTU times inch over hour times foot cubed degree Fahrenheit.
Maybe somebody could explain this to us in the comments.
I knew this when I was at UCSB. I'm sorry, UCSB. So I forgot.
So what the implication of this is going to dissipate heat a whole lot better than a cast iron part.
Yes.
And I think, and this is me speculating here, so there's a narrative around a portal, which is they have speed limits to them. And I'm guessing that part of this was the old stuff made in the 1950s that was cast. It was not ductile iron, it was cast iron. I don't know specifically what it was. It didn't have good thermal properties, and maybe they would get so hot that they would cook seals at certain RPMs. So there was a notion that you can't drive portals for long distances on the highway. And we kind of scratch our head on that and go, well, we have no problem with that. And I think part of that is the thermal properties of aluminum are so much better than of iron. And you'll see iron castings used, like a good friend of mine was an engineer at ProComp and designed a lot of their uprights, and they would use ductile iron for these castings, and they're extremely strong. And he would tell me, look, like when I did this stuff, we did brake tests, and they would bend, that spindle or that upright would bend 4 inches before it snapped. Like, that's insane.
It's pretty
so
awesome.
It's strong material, but this comes down to what are the nuances that you care about, and you can design around a lot of this stuff too. So if you know that heat is going to be an issue, then give it a larger cavity and allow for a higher oil volume content, and maybe cast fins in it to dissipate heat.
You can add a heat sink to it,
right?
All kinds of stuff.
But I think that when we start talking about castings, the one thing that I always fall back on is, what is the mission and purpose of the business in order to succeed? And I have 3 categories that I will always fall back on right now, which is, okay, what's our mission and purpose? Number 1 is make the best product that we can. Number 2, produce that stuff here in the US. Number 3, drive down the cost of the product to make it more affordable. Cost is our number 3 concern. Number 1 is quality. And I am not willing to sacrifice what I think is an inferior material for our application strictly to try to make something cheaper. And I'm not closing the door on this. I'm just saying that because this is such a new product and it's so niche, until it becomes a lot more mainstream, my only primary concern is building quality. Because if our reputation is tarnished and they build crap, but it's cheap, it doesn't matter because it's still crap. And, these are things where if we're going to look at moving to a cast product, there's a lot of engineering that has to go into the back end before you get there. You don't just take an aluminum product, make a mold out of it, pour some iron in there, and we're done. It would require enough R&D on our end that we're not closing the door on that. We're just saying that for the next year, 2 years, that's really not on the plate for us. And don't get me wrong, I would love to see our product at 50% of its current price. I can tell you that if we did that, we'd quickly go out of business because we would lose money on every single portal that we sold. They cost us more than that to make. But all of that stuff over time will come down through sourcing and higher volume and refining the process and getting a more dialed manufacturing. But to jump from point A to point B with the only consideration is cost, I think ultimately the customer is the one that's going to suffer along with our reputation. So let's talk about the other option.
Forgings. So, I mean, think about tools. If you have a cast tool versus a forged tool, I'm sure you've snapped a cast tool or a cast part here and then. They're stronger. So
where does the strength come from in a forge process? So this, let's clarify this. This technically is a cold worked part. So the way this happens is they pour out a giant plate of aluminum and then they cold work it to size, right?
Yes, yeah. And what you're doing, so pretty much every metal, when you get it from a mill, it's been poured, and then as it solidifies, it crystallizes into structures called grains. And when you cold work it, basically what you're doing is creating a finer grain structure and aligning the grains, and that's going to work harden it and give it different properties. A lot of times they'll do things like annealing it, raising it to a higher temperature to recrystallize it after that. There's a lot of different material processes that you can do to get different properties out of the same chemical composition.
So grain structure in this chunk of aluminum, so this started out as a giant plate. People call it billet aluminum.
Yeah.
And I gave up years ago and just said, that's fine, I'll call it billet aluminum too. It's technically not. This is technically plate. And plate has grain structure going in one direction. And so I can physically look at this and say the grain is running this direction. And that can be a good thing, that can be a bad thing. It depends on where your loads are coming from. And so the downside of this is it's costly to produce, it's costly to purchase, and we have a finished upright somewhere in there. We just have to remove all the material to get to it.
Yeah.
And so it's admittedly not the best process, but to go to a forging, you have to have dies made, you have to have a certain threshold of volume. It's very expensive.
Yeah.
To move our product line to a forging will cost hundreds of thousands of dollars. And I'm not saying that to like, oh, poor us. No, the end result is your cost per unit will go way down. And so when we move to forgings, and our current plan is this year not to produce a forging, but to move towards forgings. And when we do stuff, we try to move methodically and slowly, because when you rush, you make mistakes. And when you make mistakes, that can be very costly. And
Yeah.
we have a product right now that I feel is strong enough. And I think it's worth talking about, how do we know it's strong enough? So leading up to King of the Hammers, it was a Wednesday, and I got a text message from Lauren Healy about something race related. And then a photo came through and my heart kind of sank. They had an accident, and Lauren talked about this on a podcast with Chris Corbett. Chris Corbett is, I don't know what his title is. Chris Corbett is associated with Nitto Tire and sponsor of Lauren. He started a podcast. I listened to it. It's actually really good. And Lauren talked about the accident that they had. So they had a couple vehicles on a trailer, and that trailer ended up upside down, and the vehicles ended up as a yard sale several hundred yards from the trailer. And so Lauren sends me a photo of the gray Bronco that we took to Rubicon last summer that Vaughn Gittin Jr. was driving, and it was one of the test beds for our bolt-on Bronco portal. That vehicle essentially ejected at about 70 miles an hour from the trailer and was a complete yard sale. Everything on it was basically destroyed. The rear housing was bent, I think 6 inches. It had bow to it, and he couldn't actually get the rear portals off. He had to physically cut the tubes of the housing, and the whole thing sprung, and those portals came off. The front, I don't know if he broke control arms or any of that stuff. It didn't look like it from the photo, and I didn't really press too much. So we got those portals that came back to us because we said, hey, give them back to us. Let's at least inspect them. with the intention of, let's throw them on another vehicle.
Yeah.
So we have a set of those things that went through a 70-mile-an-hour rollover at, I don't know how many times the vehicle rolled, and we probably never will know because, but the thing was completely destroyed. And then you see a video that Lauren posted at Sand Hollow of this year at the United by Broncos event that he just put Rooney, the maroon Bronco, on 74 weld portals. Those are the same portals that went through that 70-mile-an-hour rollover, and they're now running on another vehicle. And let me be clear on this. We didn't change uprights. We didn't change boxes. We gave him a new set of rear axle shafts because the timeline was so quick. We weren't sure if the shafts were going to be bent or not because the housing was so bent. So I just sent him 2 new shafts and said, give us the old ones back and we'll check them later. And they're sitting in the corner. We haven't really even looked at them yet. But essentially, we took our product, we chucked it off a trailer at 70 miles an hour. We had the thing roll how many times, who knows.
Yeah.
The vehicle was basically thrown away and our product was thrown back on a new vehicle and he went out and wheeled the thing. So it kind of validates our suspicions that we chose the right materials for the right thing. And,
wild.
you know, it's unfortunate, but hey, what better way to test?
Yeah, it's a gnarly test.
Yeah. So, okay, so we'll jump back into, I guess, our future plans and where we want to see this whole product line move, which really is to forgings. And so we've already taken a couple steps internally to move towards a forged product. I know that we're going to be forging the uprights out of a 7 series alloy. I know we're going to forge the boxes out of a 6 series alloy. The reason I'm not saying 6061 is because there's lots of different options, or 7075 because again, there's lots of different alloys in those 7 series, and we will carefully and slowly work with forging manufacturers or forging houses to pick the specific alloy for our application. But one thing that you get with a forging is you get flow of grain structure, and we'll put up a graphic on this video that shows essentially a cross section that's then polished, and you can see that it's sometimes referred to as sporadic grain structure. But what happens is the grain goes every which direction and it flows through the part. And what you end up with is a far superior product due to the fact that anytime you're trying to reach that yield level, you have to overcome a compression of a grain in a certain direction. It essentially makes the part stronger than a piece that was just machined out of this. So
yeah, and that gets way in the weeds, talking about grain structure and dislocations and fracture mechanics,
and this is not something that we're going to do ourselves. We're going to work with a forging house in order to develop a specific process with a specific alloy, and it's also not something we're rushing because we know right now we have a good quality product, and the only thing that people will knock us on, they're not going to say it's not good quality. They're going to say, well, we'd like it at a cheaper price. Well, let's go back to what's our mission and purpose here. It's a concern of ours. It's that concern. It's number 3. So we'll get there, and the way we get there is with forgings. And the problem too is the dies around forgings take a long time to make, and they're very expensive. And I don't really care so much about the expensive portion of it. It's, if you rush things in this process, then you'll get what I call a black swan event. You don't know what you don't know until you realize that you didn't know it, and oh shit, now what do we do? And so we'll move in a step-by-step process, but we're not jumping to get to forgings as fast as we possibly can.
Yeah. I mean, one note on just forging tools as well. Like if you look at casting tools, you can have one match plate that you use over and over and over again it's essentially you have one tool that makes the part. For a forged part, you could need a series of progressive dies in order to get to that end stage.
Oh, that's a good point. So it would go and be mushed into a general relative shape, and then it goes to the next die and mushed into a little different and goes to the next die. And so it progressively goes into the shape that you want.
Yeah.
But at the end of the day, if you have to rank cast versus plate versus forged, it goes from forging is the ultimate best option for this. And we're starting to see this happen in the automotive industry. So the automotive industry is now across the board moving to forgings, not across the board. The automotive industry is moving to forged aluminum parts. Their reason for doing that is very different than our reason for wanting to do that. We want the ultimate strength to weight ratio. They want the ultimate weight so that they can get better fuel economy, and every ounce matters for them.
Yeah.
So, I look at, Ford's not doing it on the Bronco, clearly, because we've seen those uprights snap in half.
Yeah, that's cast iron.
That's cast iron. But they are doing it on Raptor.
Okay, I haven't seen that one yet.
And they are also,
Toyota, we had the 24.
So the 2024 Toyota Tacoma went from a cast upright, the new 23 and older is cast, it's probably forged.
Oh, it is a forged.
It's
we're
forged.
talking about the Gen 2,
Yeah,
Gen 3,
it's a forged steel.
Yeah, because you can weld it. People do the gusset kits all day. So
now they've moved to a forged aluminum upright. And I've had conversations with Toyota about this. It's for weight savings and strength to weight ratio. Aluminum is really good.
Yeah.
Rivian, I got some uprights from a Rivian. They are quite possibly the best quality forging I've ever seen from an automotive company. I was blown away to the point where I called it one of the engineers and was like, who does the forgings and what's it made out of? And got some good info from them. But yeah, the forging process is ultimately, I think, our next step. And let me be clear on this too. We're not closing the door on castings. It's just, I feel that because this is a new product to market, you really only get one chance to blow it. And that's why we're still in the form factor that we are, is because we control every single process to this, minus the anodizing, in-house. And so this is just in our wheelhouse. We acknowledge it's not the most cost effective, but let's go back to, that's our number 3 concern. There likely would be a time where I would consider going to a casting. Now, and I'll never say never, but I can't ever fathom me going, oh, we're not going to make forged parts anymore, we're just going to do cast. No, but we might look at taking all of our internals and all of our components and, okay, well, how much cost would we cut if we just went to a casting for this and this? And if the answer is substantial enough that we could save thousands of dollars, which I doubt, but we haven't done that analysis yet, then sure, I would do a cast line. But is that in the cards for 2024 or 2025? No, not currently at least. Our primary concern is dial in production, explore getting a forging process done. And the forging process, I mean, a year.
Yeah, it takes a while.
It takes a while.
And that's working hand in hand with, whoever's designing the tools and the forging house, and there's a lot of back and forth there. Everyone needs to be on the same page.
Yeah, this is something that you progress cautiously and carefully on and you'll end up with a better chance of success by doing so.
Yeah.
What did we miss? Conclusion.
Conclusion.
Oh. We already said that.
Yeah.
Our goal is to educate, give insight into how we design, and that's redundant, and educate you so you're looking. I guess it really comes down to these technical videos give you a look into what's going on in our head and where we're going with this stuff, and in what direction are we looking at, okay, we're going to pursue this, and here's why. So hopefully we look back on this in a year and we go, hey, we have a forged prototype.
Yeah, that would be badass. I mean,
Yeah.
that would be sick.
One thing we didn't cover, I guess, was numbers regarding direction of grain flow. God, do we want to dive into the weeds on that?
I mean, probably like if we're looking at what we're actually doing in house, for the most part, we're treating materials as isotropic, which means uniform in all directions. I mean, we're using FEA software. It's an additional.
It's a little bit of additional, and I've said this before, that FEA is the best and worst thing that's ever happened to engineering.
Yeah.
Because it gets oversimplified. So, no, we're not going to dive into FEA today. All right, well,
cool.
We appreciate the lengthy time. Sorry. we get rolling and don't want to stop.
Yeah, exactly.
But,
if we have any forging engineers watching, hit us up in the comments. We had some good ones from the bearing video. So.
If you're a forging engineer and you work with a domestic forging house, we would love to talk with you.
Yeah.
We're exploring a couple forging sources right now, some up in the northwestern US. There's a forging house in Los Angeles. If you're an expert on this stuff, we're not experts. We know enough to be dangerous. We want to talk with you.
Yeah.
So email us at info@74weld and title it forging, or we're a forging house.
Yeah.
We'd love to talk with you. We want to keep forgings here in the US if possible. There is still good forging houses here in the US.
Yeah.
So reach out to us.
Yeah.
We'd love to chat with you. Until next time.
Yeah.
Thanks, guys.